Pandas is a super powerful data analytics library in Python. It can handle huge datasets by default, but with a bit of technique and finesse, we can make it even more efficient. Hey folks, I'm Trent. I'm a data engineer with 5 years of experience, and in this video, I wanted to share with you 3 different techniques that I use to make my Pandas application super efficient in their memory usage. To keep things practical, I'll take us through an example scenario and a dataset that I found on Kaggle to illustrate the different techniques. Alrighty, let's jump right into it. The dataset that I'm going to be using is this one from Kaggle. I'll leave a link to it in the description. It is a dataset of hotel booking demand. So in it, we've got information like which hotel a booking is being made at, whether or not that booking was cancelled, the lead time, some guest information, when the booking was made, etc. We'll take a more in-depth look at it in a second. So jumping over to my editor, I've downloaded and decompressed the data into a CSV file and set up a notebook over here just to explore the data a little bit and illustrate the techniques to you. So to start things off, I'm going to import Pandas as PD and then set some options to make things a little easier to read. Just to take you through our example scenario, let's say that a data source team gives us full extracts of this hotel CSV data, and the analysis team that we're giving data to wants to create reports for the following: bookings with a lead time higher than 50 days. The booking details of interest are the hotel type, the arrival date, guests, customer type, cancellation status, and lead time. So effectively, our application needs to take the full data set and reduce it for the analysis team. Let's read in our data by using the Pandas read CSV method and take a look at a small sample of data. Should probably run my imports first. Let's do that. So let's retry reading the CSV. Alrighty, and we can see a more detailed view of our data. So looking at it, this is quite a wide data frame, quite a wide table, right? But it has all the information that we could want about a hotel booking. You can see some of the information already that we're interested in, such as the guest information, so how many adults, children, and babies there are checked in the booking. And if we scroll all the way to the side, we can see the customer type as well. Great, let's take a look at how much memory this data frame is using. So something to note in Pandas is that when you read in data, it is all read into RAM, right? So this is being held directly in memory. By using the df.info method over here and specifying that we want to look at the exact amount of memory used by specifying memory usage equals deep, we can take a look at how much memory this is consuming. At the top here, we can see we've got about 120,000 entries, so 120,000 records. So kind of big, not super huge, but kind of big. We've got 32 columns, that's pretty wide, and it shows us information about each of our different columns over here. One thing to note is that some of the columns are missing data. We can see that the company column over here is missing quite a lot of data and only has about 7,000 non-null values. This isn't one of our columns of interest, but useful to note. You can also see that agent is missing some data. If we scroll down, the point of interest for us is actually this memory usage statistic over here. Currently, it is using 93 or roughly 94 megabytes of data in memory. So let's take a look at the actual data by using the dataframe.describe method over here. This should show us some information about our numeric data in the dataset. We can see things like is cancelled, and it has a max value of 1, a minimum value of 0, and that is expected. It's just a binary value telling us whether or not a booking was cancelled. And we can see some other interesting stats over here. Let's take a look at some guest information and see that the maximum number of adults in a particular booking was 55, and maximum number of children and babies was 10. Pretty big family, right? But we can also move on to our non-numeric data to gather some information about that. And we can see that hotel, for example, has only got 2 unique values. we scroll down to the side, we can also take a look at another variable of interest or column of interest. That is the customer type, which has 4 unique values in it, with the most frequently occurring value being transient. All right, so we've got a good idea of our data now, or pretty high level idea of our data. We need to write our application to process this data for our analytics team. So I've captured that in this file over here, basic pipeline.py, and let's go through that. So scrolling through, we can see in the main method over here, I am specifying 3 different functions, the extract, transform, and load functions. If you're familiar with ETL pipelines, this is just a really simple version of one of those. So effectively, I am running an extract. Let's take a look at that. And in this extract function over here, I am just reading our data using the read CSV method. If we take a look at the transform function, you can see I'm performing 2 different steps. One of them is data cleaning. Let's take a look at that. All I'm doing is filling blank or missing values with a 0 value. This is a really oversimplified cleaning function, but it serves a purpose for now. And the second thing I'm doing in the transform function is doing a lead time filter. So if you remember, part of our scenario was to filter the data for records that had a lead time greater than 50 days. So that function over here is now taking our data frame, taking the lead time and filtering by a particular filter value that we specify down here. So we've made it 50 as per the requirement. And all I'm doing is copying that as a completely new data frame and returning it. And then finally, our load function, which is going to write our data out as a CSV file. All I'm doing here is selecting the columns of interest according to our scenario and writing that out to a CSV file called highleadtimebookings.csv and excluding the index. And that's our setup. I've just specified our file path over here so that we can extract the data, transform the data, and then load it. Down here, I'm just stating that when we run this application, we should run the main function over here. So let's give this a run and see what we get. Let's Python basic pipeline.py. And after running, you can see we get some output data for the highleadtimebookings.csv. Just taking a look at it, you can see we've got our columns of interest and our data over here. This application works fine, but let's get an idea of how much memory it's using by leveraging the Python library trace.malloc, which comes with the Python standard library, so no need to install anything. So I've imported trace.malloc over here, and let's add some code in the main function to gauge how much memory is being used. So what I've added to the main function over here is a trace.malloc.start for trace memory allocation and start tracing the memory allocation. And down here, after we've done our ETL or extract, transform, load, I'm going to trace the current and peak usage of memory by using the method getTracedMemory, and then print out the current memory usage, so the memory usage at that point, and the peak memory usage that occurred between our start and when we snapshotted the memory being used. Then after all of that, I'm just stopping the trace.malloc. All right, let's run our application again and see how much memory is being used. We can see that the current memory usage, or the memory usage at that point in time, was about 50 megabytes, but the peak was around 104 megabytes. Now that we've got a baseline, we know what to work towards. If we can do better than a peak of 103 megabytes, we've already reduced our memory allocation and thus increased our application's efficiency. So our first technique to save on memory is to read what you need. We should only consume data that we are actually going to use in our applications. This may sound obvious, but it can often be overlooked because of how convenient it is to read data in Pandas. You can achieve this by using the useCalls argument in the readCSV method. What this does is it simply picks out the columns that we specify and leaves the rest behind. It does not load every single column into memory. So using this argument, let's create a new data frame called smaller.df and get a sample of that. We can see this has only read in the columns that we specified. And these columns are exactly those that we need to fulfill our scenario request: the hotel, the arrival date, number of guests, the customer type, whether or not the booking was cancelled, and the lead time of the booking. So reading that in, let's go ahead and look at our memory usage. So we can see all of our different columns. And over here, our memory usage has been reduced to 26 megabytes. That's less than a third of what we were using previously, which is a massive saving for such a simple argument to be added to our read CSV method over here. All right, let's apply this in our pipeline. To do that, I'm actually just going to steal this code over here and paste it into our extract function. With use calls in place, let's rerun our application to see if we've actually saved any memory. All right, we can see that we saved memory on the current memory usage, and in this case, current memory usage in the main function is recording right after the load function was created what the memory usage was. So we've already saved memory over here because it is doing less in the load function because there's less data to process. And the peak was only 30 megabytes, which once again has taken us down to about 1/3 the memory usage we were using before, or 1/3 the peak memory usage we had before. Now, this is great and super simple to apply, but we can do even better with our second technique. Technique number 2 is to use efficient data types. Numeric data are the easiest to reduce and to understand conceptually. Under the hood, data is represented as bits, so ones or zeros, and Pandas reserves the highest number of bits by default as a guess as to how to store your data. I've got a table over here showing you the min and max values of different numeric data types, integer and float, to illustrate the point. So if we take a look at this, you can see that an 8-bit integer can have a maximum value of 127 in decimal, or in our usual numeric notation that we're familiar with, and a minimum value of negative 128. If we go all the way up to 64 bits, you can see we get about like 9 quintillion as the max value and negative 9 quintillion as the min value. For floating point numbers, it's a little more complicated because of the decimal points. These represent rational numbers, whereas integers represent whole numbers. But for a floating point, you can see we get a pretty big number for a 32-bit float, but an even bigger number, times 10 to the power of 308 over here, for a 64-bit floating point number. Now, thinking about this and knowing that Pandas allocates the highest or biggest representation of a number by default, this can be a bit of overkill, right? Looking at our data and what our data represents, I don't think anybody's going to be checking in 9 quintillion babies, or at least we can hope they're not going to. And so we can do way better on our data type allocation by being specific and telling Pandas what data types to actually use. So to illustrate this, I've set up a more efficient schema for us over here as a Python dictionary and specified each of our columns. Notice that our different numeric columns now have more efficient data types. Actually, to illustrate this, let me go ahead and grab our df.info again, so this is close by, or I think we called it smaller df.info. Just to examine this, you can see that a column like the number of guests are stored as 64-bit numbers. So Pandas by default is reserving 64 bits to contain each element of the data. All right, so going along with our more efficient schema over here, you can see that I've specified things like the arrival date year as a 16-bit integer, the arrival date day of month as an 8-bit integer, because you can never get higher than the 127th of a particular month, the number of adults as an 8-bit integer, the number of children as a 16-bit integer. Actually, I'm not happy with that. Let's make that an 8-bit integer as well. And the number of babies as an 8-bit integer once again. Over here, I'm just taking our smaller data frame from our previous technique example and filling in the null values with a 0. Then I'm making a new data frame called castDF, taking the smaller data frame and casting it using the asType method and feeding it our schema dictionary that we formulated over here, and just copying this into, or creating a copy of this as the cast data frame. Let's take a look at that. I have not run our schema, so let's run that. And we can see we get our data, looks the same as before. Even if I scroll through this, it looks pretty much the same. But let's take a look at the memory usage now. And just as a reference, I think we had it up here. Okay, this is giving us an estimate. Let's go ahead and specify memory usage as deep. And we can see that our reduced dataset is about 26 megabytes. And if we take a look at our dataset with specific data types, this has been reduced down to about 20 megabytes or 21 megabytes, which is pretty great. We've reduced down our data by quite a big factor at this point, but we can do even better with efficient typecasting. In order to illustrate that to you, I need to explain a different data type, which will deal with our objects over here, or object data types. So, for example, hotel is stored as an object because it is string data or text data, and even the customer type, as well as the arrival date month, is stored as an object. To store object or string data more efficiently, there is a data type in Pandas called a categorical data type. Categorical types are best used for columns with a low number of unique values. The technical term for this is low cardinality values. Basically, Pandas creates an index in the background for your unique values and points back to that index instead of the original data. I've actually drawn a simple diagram to illustrate this point to you. Without the categorical type, our data frame looks something like this. Looking at the hotel value, and let's zoom in a little, looking at the hotel value, we can see that our data, the unique values of resort hotel or city hotel, are stored directly in the data frame. This is without the categorical type and the default behavior of Pandas. But if we include a categorical type, what it's doing at a high level is creating an index over here to map resort hotel, for example, to the number 0 and city hotel to the number 1. Then in our data frame, how it's being stored under the hood is with these zeros or ones. And zeros and ones are way more efficient to store than these long strings of RES, etc., being stored directly in the data frame. But from our perspective as a user, we don't see this. Pandas lets us use the data frame as usual, which is pretty awesome. With that in mind, if we take a look at our different object data types like hotel, the arrival date month, and the customer type, these are low cardinality columns, so we can reduce the size of them using the categorical type. They qualify as low cardinality because hotel only has 2 unique values, the arrival date month has only got 12 unique values, and the customer type, as we saw earlier, only has 4 unique values. If we had information like customer names, its cardinality would be close to how many records we have, because names are generally pretty unique and repeat customers won't be as frequent as we would expect, or you're not going to have a single customer or 2 customers doing all the bookings, or at least hopefully not. So these all qualify to be categoricals, or we could benefit from using categoricals. Let's try that out and see what we get. So going back to our schema up here, I'm going to select all of the object types and specify these as category types. Let's rerun this to update our schema dictionary, update our cast, and we can see the data looks as normal. For example, hotel is still resort hotel or city hotel. And if I scroll to the side, customer type looks the same, arrival date month still looks the same. So from our perspective, the data has not changed. But let's take a look at the memory usage. And we can see that the memory usage has been reduced down to 1.5 megabytes. So from our original data frame of about 90 megabytes to roughly 1 megabyte, if we round down, we can say that we've got a 90 times improvement in memory efficiency, which is pretty awesome to see, right? I mean, this wasn't that hard to do, and already we've got a performance improvement by a factor of 90. All right, so now that we know this technique, let's go ahead and apply it in our pipeline. So taking our basic pipeline, the place where we're going to do this is actually in the transform step. I think that's most appropriate. And to do that and add a little bit of finesse, I suppose, is let's store our schema in a file called schema.json, for example, .json over here. Let's steal the schema from our notebook. Now we have our schema saved in a JSON file. To read in our JSON file, I'm using the syntax of with open schema.json as if, and then using the json.load method over here to get hold of our schema. I actually don't want to print the schema. I want to close the file. And in order to use this, we actually need to import the JSON module. So at the top here, I'm just going to say import JSON. All right, things are looking good. Then I'm going to pass this schema to our transform function over here. Schema. Let's jump over to transform, specify that we can actually give it a schema. And post cleaning, let's go ahead and say df equals df.asType schema to cast. We've incorporated the two techniques discussed thus far into our application to make it far more memory efficient than it was originally. The last technique I'm going to discuss with you is the most complicated out of the three, but is incredibly powerful when used in the right scenarios. The technique that I'm going to share is chunking your data. The first technique we used was selecting a smaller number of columns. Chunking is a technique for selecting a smaller number of rows. To illustrate this, I'm just going to bring up a simple diagram that I have over here, just to illustrate the idea behind chunking. It's a little abstract, so bear with me. The usual process of reading in data into a data frame runs something like this conceptually. We have our CSV file, and all the data is contained within that CSV file. We read all of that data in one go and process it all together and output it all together in one shot. Chunking, on the other hand, splits our data up into chunks, so subsets of rows of data. You can think of this as having multiple chunks. So for example, here I've got 3 different chunks, and these get processed one at a time. So chunk 0 will go through our process and then be written. Subsequent to that, chunk 1 will be processed and then written, and chunk 2. To illustrate this technique, I've got a code block over here specifying that df_chunks equals read CSV, pointing at our CSV file, but now I'm specifying an argument called chunk size and made it 1000. This number represents how many records I want in a particular chunk. Let's take a look at what this returns when I run it. So this doesn't return a data frame, but instead returns this text file reader object. The way I like to think about this is when you go to the grocery store, you first compile a list of groceries and then go and buy those groceries one by one. Well, if you're organized, I normally forget my grocery list at home. But besides that, it's kind of like having a list of items to go through. You don't actually have those items on hand. You instead have a reference to those items. And that's kind of what the text file reader is doing over here. It is not the data itself, it is instead pointers or references to the data sitting in the file. If I take this dfchunks object and use the next keyword to get me the first iteration of the dfchunks value, we'll see that it actually returns a data frame this time. In this case, if I scroll down through it, you can see that we get 1000 rows by 32 columns. And this is exactly the number of rows we specified when stating that we wanted to chunk out our data frame. Chunk size equals 1000. And you can see that the index goes from 0 to 999, so 1000 records. If I hit next again on dfchunks, we will get the next 1000 records. So this index, or these indices, go from 1000 to 1999. So each time we call dfchunks using the next keyword or looping through it, we would get a different chunk of data and process it that way. And you can already probably tell that this is way more efficient because you're only reading a small subset of data into your application at a time. This does add some complexity because now you have to think about looping through each chunk, right? You can't just do everything in sequence. So the pattern we would need to follow is to loop through by doing something like for data frame in df chunks, perform our process on that chunk of the data frame. Let's apply this practically in our pipeline. To do that, the very first function we need to modify is the extract function, where extract no longer is going to return a data frame, but is instead going to return chunks or df chunks. And let's specify a chunk size of 1,000. I'm happy with that, and we're going to return our df chunks object. Then in our main function, no longer can we simply call each function on top of our data frame. We need to create a for loop to go through each chunk. To do that, let's modify our code by saying for df in extract, because extract returns a df chunks object or that text file reader object that we can iterate through, and then perform our transform and load on each df chunk that's being passed through. The last thing to note is that we also have to modify our load function in this case, because if we left it in this state, it would simply overwrite the CSV every time with a different chunk every time we called it. So we need to change the mode in which we are using the toCSV method. So we can specify mode equals A for append, so that data is not overwritten every time you call the writer toCSV. It is instead appended to the bottom of the file. So that's just something to note when you are using the df chunks kind of method or the chunking technique. Also going to remove this filter because it is unnecessary, because we are already filtering our data. And that looks good to me. Let's run our application again and see what the memory usage is like now. And man, we can see that we've saved a ton of memory. The current memory usage right after the load, right after the last load, is only 0.2 or about 0.25 megabytes. And the peak was only about 1 megabyte. We've improved our application by a factor of 90 times the efficiency it was using before. While this technique is great, it does add some complexity to the code, as we've seen. So I only use it if I really have to, but it is still super powerful to be able to process data piece by piece by piece. So we've covered 3 different techniques that I often use to make Pandas highly memory efficient. These were reading what you need, using efficient data types, and then chunking out your data. I'm interested to know what your biggest challenge is working with large data sets in Pandas. Drop your questions or share your experiences in the comments below. I'd love to hear about your scenarios and discuss more solutions. If you enjoyed this topic, I have another video on using Python for data analysis that you can check out. If you found these techniques useful or interesting in any way, please give this video a like and consider subscribing to the channel for more insights into data engineering and data analysis. Thanks again for watching, and I'll see you soon.